We're on the cusp of a revolution in transportation. It is very likely that in the next few years, autonomous vehicles are going to become the norm. This should make driving significantly safer than it is today. Research suggests that if the cars in the United States were autonomous, or if 90% of them were autonomous, then accidents should drop from 6 million a year to about 1.3 million a year. And deaths should fall from 40,000 a year to just over 11,000 per year. There should also be improvements in timing and fuel efficiency. At least one study suggests that autonomous vehicles would lower the CO2 emissions by 300 million tons per year. We're at a similar place with the potential to transform how we use the skies. This is being led in large part by retail fulfillment. In a pilot test last summer, Amazon Prime Air used autonomous drones to deliver packages to customers. And within 30 minutes of an online order, the drone had delivered a package to a customer's home. The cost of that service was only $1. In other words, the sky really is no longer the limit. So we can actually imagine a search and rescue team that can deploy a drone, that can use a cell phone signal, find its way through difficult terrain, and deliver medical supplies to an injured hiker. The key to realizing this potential is to understand that these vehicles have to be self-piloted, self-guided, and with online situational awareness. Why these properties? Why can't we just have it controlled centrally? For example, airplanes right now are largely controlled by a centralized air traffic control system. Well, there's at least two challenges, significant challenges, to having a centralized control system for autonomous vehicles. The first is that there will be latency. There will be a delay, in other words, between the signals sent from the vehicles to the computer and back. But a more substantial concern is that a centralized system could be hacked, and such malicious hacking could have catastrophic consequences for the whole system. Designing robust control programs for autonomous vehicles is not a trivial task. There are several paths we can take to get there. One is to use traditional engineering approaches, use trial and error to iterate through and gradually improve those vehicles. But there might be a shortcut that is available to us by observing nature. If we can study animals that fly and understand how they do it, we can take advantage of hundreds of millions of years of evolution and potentially leverage this information into motor vehicle design and control. And let me give you an example as to why that might be useful. Consider moving through the environment. You have to create forces, but you also have to balance them and control them to make sure that you're not unstable. Think about a human walking on the earth. As we walk through, we are generating forces, and most of that force is imparted to the ground. But the ground's a big object, and for every force that we impart to it, the ground returns an equal and opposite force. This is called the ground reaction force, and it aids incredibly in stability. But what about animals flying in the air? They don't have ground reaction forces. What that means is they must balance all of the forces they produce, and they must do this in real time, in a rapid fashion, from the moment they take off, as they fly forward, navigate clutter, reach a goal, potentially avoiding predators and competitors along the way. So for over 20 years, we've been studying how the muscles generate electrical signals that go out to the wings, how those wings make motions, and how those motions lead to flows and forces that propel the animal through the air. But in this research, I've always had to treat the brain as a black box, for the simple reason that we don't know the role of the brain in avian flight control. Or rather, we know what it does in essence, which is that it takes a lot of sensory information, vast streams of sensory information actually, and rapidly transforms them into motor programs that allow the birds to do all the incredible things they do. But how that transformation from sensory information to motor commands happens is basically unknown. To make progress on this front, my laboratory has developed several new approaches. One of them is to use virtual reality, in which we can track a flying bird while showing it different motions. In this movie shown here, we're displaying a moving spiral, which is a disruptive stimulus to a hovering hummingbird. As it attempts to feed at this artificial feeder, it's pushed back by that disruptive stimulus. Using experiments like this one, as well as a number of follow-up experiments, we demonstrated a simple program that hummingbirds use to hold their position in flight, which is that they sum all of the information in their visual field and respond accordingly. This works well for them in nature, because in nature, even on a windy day, if there's lots of motion, the motion is so complex that it tends to sum to zero net motion. And so by summing across the whole visual field, they're able to maintain something quite stable. But what's interesting about it is that they are sensitive to all of the different directions. They can monitor motion in so many different directions simultaneously. It turns out that itself is an unusual feature that seems to be unique to hummingbirds. So in this example that I'm showing you here, we're moving dots in different directions, but sometimes pausing them. And as we're doing this, we're recording from the brain, seeing how the neurons respond to this type of motion. All of these neurons, or most of these neurons, have a very strong preference for certain directions and for certain speeds. And as you might imagine, in tetrapods, or in humans and in other land vertebrates, we see that most of those neurons are responsive to global visual motion, including in the zebrafinch, as shown here. But in studies with hummingbirds, we've demonstrated that those same neurons are actually responsive to a much wider range of motions. Any one neuron has its own direction preference, but across the whole brain, we see lots and lots of neurons responding to lots of different directions. Therefore, this is a neural mechanism that actually provides an explanation for the robust motor control program that we saw in the hummingbird hovering in the virtual reality chamber. So if we're really going to move from understanding how sensory information is taken in and then transformed into a motor program, we also have to develop new tools so that we can merge behavioral and brain approaches. So in my lab, we've been trying this with two ways. The first one is a technique called optogenetics. And what optogenetics allows us to do is to use light to actually turn on or turn off neurons in an awake and behaving animal. And with this, we can test the hypothesis that global motion neurons are in fact underlying this robust motor program for hovering. The other technique we're using is to move to much more enhanced virtual reality with flying birds, to create a virtual reality system in which the bird is tracked in real time, and what it sees or what we project to it can be manipulated also in real time or in close to real time, so that we can also delve much deeper into the behavioral algorithms it's using to accomplish different types of flight. And now imagine if we can employ those sorts of algorithms in a self-driving car or in a self-piloting aircraft. What could we do with it? Well, let's bring an example close to home. Here in the Pacific Northwest, we're all very nervous about something. There's sort of this impending danger that we're aware of all the time, and that's of the big earthquake. We live near the Cascadia Fault, and a lot of experts believe that we might be overdue for the big one. What will happen in that scenario? Well, it's going to be bad, and it's quite likely that there will not be the conventional support that we're used to. It's going to be so wide and so devastating that we can't expect the military to reach us. So who will help us? Well, imagine if we can create a fleet of drones that upon sensing a magnitude earthquake, say 6.5 or better, takes to the air. They don't need a GPS system. They don't need cell phone signals to know where they're going. They can navigate unknown terrain, treacherous terrain, and deliver medical supplies. Also imagine another set of drones, maybe fixed-wing drones, that can take to the air and establish a cell phone signal that can connect those of us on the ground to the rest of the outside world. There are tremendous potential for these sorts of vehicles in driving and in flight and for convenience, but it will require major advances in automated control. Understanding the brain circuitry that birds use to control flight has particular relevance because of their size. They're about the size of drones, meaning that a collision with an object or the ground will have similar catastrophic consequences. And we expect that the brain algorithms are tuned accordingly. It is likely that birds will have a lot to tell us about how we can program computers to do the same.